Example 5, this is our last example. So similar to example 2, remember in example 2 we talked about dropping a ball from a height of h, or height of 12 meters. We've got the same mass and the same height as we did in example 2. So we drop a ball 12 meters, it's going to be the mass of the ball times gravity, because that's the force of gravity, times the height that it falls, and cosine theta just winds up going away, turning into 1, because cosine of 0, because they're parallel, is just 1, so we can just pay attention to the force times the distance, so mgh. Okay, great. What about this case? A ball of mass 0.25 kilograms is tossed out of a window at a height of 12 meters. So now it travels up and then travels down. So we don't know how high it gets, right? And I didn't tell you precisely what it was. It could be that it winds up getting really tall, or it could be practically flat and then falling immediately, right? It could be either one of these. I didn't tell you how it's going to look. So how can we figure out what it's going to be? Well, remember, we know about how negative work works. Well, notice that for the amount up here, for this portion right here above the height of the window, no matter what happens, the ball is going to wind up going positive, let's call it capital H. So there's the H that it falls to the ground, which will be little h. That's the amount that we're guaranteed. And then there's capital H, which is the variable amount that it winds up going depending on how we throw it. So it has to go up by h, but then to be able to make it down, it has to also go down by h, right? So we've got a positive h and a negative h. Well, what happens if we look to the work done over the positive h and the negative h section? Well, while it is traveling to the side, gravity is only going to be caring about the component of up and down, because everything else is going to be perpendicular, so we can just toss it out. So we only have to care about the up and down components. So positive h is the amount that it travels up. That's the parallel amount, the perpendicular amount. The motion sideways we can just, get rid of because it doesn't matter. That's the amount that is perpendicular, and we can throw it away because work only cares about the parallel amount. So in this case, we only have to care about the up by h and down by h, capital. The up by capital H and down by capital H, and then the little h. Well, we already know that the amount of work done in the little h is going to be mgh, right? Well, what about the amount of work done by the capital H? Well, this one, g, is negative, right? G is a negative number, yeah? Okay, so positive h, if we go this way, they're actually going to have an angle theta equals 180 degrees. So this is going to give us negative mg big H. What about the direction where it goes down? Well, that's going to be theta equals 0, because now they're going in the same direction. So this is going to be positive mg big H, right? We've got the idea that you go up by some amount of height, but you're fighting against gravity, so gravity is taking work out of the system, so that means a negative work. So negative mg, the amount you travel up. But then we wind up having to travel the exact same amount down if we're going to make it to the ground. So that means that that amount that we just lost in work is going to be regained in work. The capital capital H mgh is going to wind up canceling the negative mgh. The two are just going to hit each other and they're going to disappear, and we're going to wind up getting that these two things just cancel each other out. And in the end, the only thing that we're left having to care about is the h that we got right here. That's the important part. Mg little h. So no matter how crazy a throw we have, if we go way up or it's really flat, it doesn't matter, because the amount of work done by the extra arc from where the amount that isn't just where it starts falling, the 12 meters we're guaranteed, is going to be canceled out. The two works go opposite one another, so it just gets canceled out. So in the end, it's mgh. So in the end, our answer is just going to be the exact same answer we got for example 2. The work equals mgh, which is going to be 0.25 times gravity, 9.8, times the 12 meters, which equals 29.4 joules. What we got. And the reason why is because the amount of the arc that goes above where we started gets canceled out, because it winds up having to travel up, but then it travels that same amount back down before it can do the real fall of little h. So the capital H's wind up canceling one another out, because they do the same thing and they're dealing with the same gravity, but they go in opposite directions, so they just cancel one another. And so all we have to worry about is where we started if we want to figure out the amount of work that gravity is going to put into it when it hits the ground. All right, hope you enjoyed this. Hope you got a good understanding of work, because it's going to be really useful when we get into energy in the next section. See you later.